Now, good morning, everyone. So previously we have discussed the single line to ground coupling. Now in the previous lecture, we have shown the carrier coupling on a single line to ground basis. The question arises that is this coupling a wise choice? Statistically, if you see, majority of the faults are the line to ground type of the faults, and further in the power line carrier communication, the information has to be passed over the power line itself. So therefore, during the fault, when the carrier is needed the most, the carrier will have to be passed across the line to ground fault, and this is actually bound to cause a severe attenuation of the carrier signal, rendering it unusable at the remote end. So line to ground coupling is not a very sound choice as far as carrier coupling is concerned. So another type of coupling is the line to line coupling. So figure here shows the line to line coupling. In this case, you will see it is actually the line to line coupling, coupling on line to line basis. The carrier signal propagate through the air. The carrier signal in this case, it propagates through the air between the line conductors, and therefore the attenuation in this case is much less. And this mode of transmission, which is also known as the, we can also say it as the aerial mode, AERI, aerial mode of the transmission, that is line to line, and it actually results in a much better performance during the single line to ground fault. Now let us discuss the unit type carrier aided directional type relaying. Now in this case, the protection, this protection scheme, it takes the advantage of the fact that as the fault location changes from just ahead of the bus to just beyond the bus, the nearest directional relay sees a sharp change in the fault direction, whereas the remote relay, so it is based on the fact that whenever you will say that whenever the fault takes place, the nearest relay sees a sharp change in the nearest relay. It actually sees the sharp change in the fault direction. However, if you see a remote relay, it does not see any change in the direction of the fault. The remote relay cannot tell whether the fault is within the line zone or outside it, whereas the nearest relay has no difficulty at all in discriminating between the same. So the information about the fault direction as seen from each end is conveyed over the power line carrier to the another end, as you have seen here. At each end, simply we will have AND gate here, that is we will ending it, and the contact of the local relay with the status of the contact of the remote relay give rise to a unit type of directional protection. So this type of protection is known as the directional protection. Now from here you will see here we will have the internal fault. Now for this internal fault, AND gates at both the ends become enabled, and it instantaneously trip the associated circuit breaker, because in that very case we will have the one signal here, and because the fault is internal in that very case, so it will trip the associated circuit breaker. This generates a well-defined zone of protection consisting of line length between A and B. Now another example, let us suppose that we will have the external fault. It shows an external fault since one input, in this case one input of each AND gate is low, that is this is low and this is low. So finally what we are getting the 0 as an output. So both the AND gates in this case are disabled, and unit scheme restrains on the external fault. So from this you will see that there is actually the absolute selectivity as far as ends of the zone are concerned, giving rise to a well-defined protective zones, and this scheme is you can say that we have discussed is known as the unit type of protection. So it is known as the unit type of protection, and both the relays use the directional principle, and it is known as the unit type directional protection. Unit type directional protection. It is known as the unit type directional protection. Now we will discuss the phase comparison relaying, which is known as the unit scheme. We will discuss its concept. In this type of relaying, we actually explore the we exploit the phase shift undergone by the current at the end which is nearest to the fault as the fault changes from the internal to the external. Now you can say that the end which is far from the fault cannot have any change in the phase of the fault current as the fault changes from internal to external, but the end which is closer to the fault sees almost a 180-degree change to the phase current. As it is clear from this, you will see that let us suppose that we will have this external fault is there, and then in that very case it is moving in this particular direction, it is feeding that external fault. Now let us suppose that fault internal is there, so this is this remote and the direction of the current is same, however the direction of the current is changed. So we do the comparison of these two currents in that very case. Now the local and the remote end currents can be arranged out of phase for external fault or the load condition. So these are actually, here it is shown that it is in phase, however we have to arrange the CTs in such a way that it is out of phase for the external fault or the load condition. This can easily be achieved by selecting the appropriate CT windings as a reference. While selecting the appropriate CT winding as a reference, we can have the external current and we will have the internal current like that as shown here, that is these are 180-degree out of phase with each other. However, the phase shift will not be exactly 180-degree, but maybe lag this position by a small angle. Let this small angle be plus minus delta, representing the load being carried over the line. Now as the fault changes from the internal fault to external fault to the internal fault, the current at the nearest end will undergo an appropriate that is approximately 180-degree change in the phase shift and will be more or less in phase with the remote end current as shown here. No, we will have the internal fault, that is IB internal and IA external. However, in this case it is shown that these are 180-degree out of phase. However, we are connecting the CTs in such a way that these are in phase with each other. Now if we measure the phase shift between the current at the two ends, then we can easily decide whether the fault is an internal fault or the external fault. Now let us take a case, let us assume delta to be 20-degree, then any phase shift between 0 and plus minus 160-degree will indicate an internal fault. Let us suppose that delta be 20-degree, this 20-degree. Now let us draw a diagram. Now let us suppose that we have IA here, and in this case we will have the IB. Now then we will have this circle is there, and this, let us suppose that this angle is plus minus delta, which is equals to that we have taken as 20-degree. So this region is actually because these are out of this phase, so this region is the you can say that this is the restraint region. And this region is the trip region from this scheme. This region is the trip region, and let us assume that we will have a 20-degree of delta, and any phase shift between 0 to 160-degree will indicate it will indicate an internal fault, because it will indicate this is 20-degree, so it is totally 60 degrees, so it is plus minus 60 degree, whole of that angle. So it is an internal fault, and a phase shift of plus minus delta give rise to an coincidence period of, and the coincidence period in this case is calculated by, that is Cp is equals to 180 degree total minus delta into 20 degree, that is what is delta divided by 180. So it is 2.22 milliseconds. So in this case the Cp is 2.22 milliseconds, and here also Cp we will get 2.22 milliseconds. So for a phase shift of 100 plus minus 160 degree. Now we can explain this physical implementation for the above mentioned concept. Let us suppose that we will have, let us take the diagram, and in this case internal fault is shown. Each end from this you will see that end A, each end sends the carrier only during the positive half of the cycle, as you have observed from here. So positive half of the time period of the power frequency AC wave, and this results in the generation of the modulated carrier sent by the end A for internal as well as external faults. So this modulation can be easily recovered back by the by the demodulation strategies, so to get a square waveform as the output. Now from this you will see for internal fault, in this figure it is shown that the demodulated square that is square waves are exactly coincidental, and the let us suppose that the coincidence period in this case is 10 milliseconds on 50 hertz basis. That is, here the end A current for internal as well as external fault, then the modulated carrier sent by the end A for internal as well as external fault, then this is the demodulated wave, this is the second wave, and B modulated carrier, and this is the demodulated wave, and finally we are getting the coincidence period pulse obtained by ANDing these first and second. We are using the AND gate, and finally what we are getting, the coincidence period in this case is nearly that is very small. Now so finally what happens, that output is there in that very case. Now let us discuss the external fault. Figure here shows the external fault. Again the two ends generate the carrier only during the positive half of the frequency, as you have seen. So this is the end A current for the internal as well as external fault. This is a modulated carrier sent by the end A for internal and external fault. This is the demodulated. Now end B. From this what we observed, as we will have it is the fault is external, so the direction of the current changes, so it is 180 degree phase. Now previously it was here, now it is here, so they are 180 degree phase. So here we will have the modulated carrier sent by the end B during the external fault, and the demodulation of the end B carrier recovered at the end A. Now from this we will see, because of the phase shift, now the demodulated square waves do not have any coincidence at all, or the coincidence period in this case is nearly about 0. Now this coincidence period can be easily found by ANDing the two demodulated carrier wave, and as a result no coincidence is there. So in this case what we see, no output is there. So definitely what it do, it will restrain, because the this coincidence in this case is no coincidence or less coincidence, as it is clear from this diagram. That is, we will have this. Now finally what we are getting. So coincidence period can be easily obtained by ANDing the two demodulated wave, and if the coincidence period is greater than the certain threshold, we can either use any of the digital methods to follow the simple so we can use any of the digital method to integrate the scare wave and comparing it with the some DC value which represents the desired threshold. So that can be that can be implemented by this also by using this comparator and with the set threshold as shown here. So it is actually the hardware to measure the coincidence period. It is the hardware to measure coincidence period. So this is all about the carrier related protection. The next lecture we will start with the generator protection. Thank you very much.